Hi, my name is Peyman Jabbazadeh, and I'm going to talk about some fundamental problem in graph theory. And all of them are a generalization of the minimum spanning tree problem, and all of them are NP-hard. So let me start with the minimum spanning tree problem. The problem give us a weighted undirected graph, and we want to select a subset of the edges of this graph such that it span all vertices. We want to find a tree such that it connect all vertices together. For example, here we have this graph, and we selected the green edges, and it connect all vertices together. And the goal is to select these edges such that the total weight of these edges become minimized. And there are many algorithms for this problem that find the optimal solution. For example, Burowka, Prime, Crosscut, and a lot of more. So this problem is not anything hard, and we can find the optimal solution for this one. But here I want to talk about generalization of this problem, which all of them are NP-hard. So I will start with Einstein theory. Then I will talk about Einstein forest, which is a generalization of the Einstein theory. Then I will talk about Peirce-collecting Einstein forest, and then Peirce-collecting Einstein theory, and then KMSC, and finally K-Einstein theory. So let's start with Einstein theory problem. So what is the Einstein theory problem? So in Einstein theory problem, again, we have a weighted graph. And in addition, we have a subset of vertices that we call them terminals. And the goal is to find a tree spanning all of these terminals, connecting all of these terminals together, such that the weight of the edges that we have selected is minimized. So for example, here the squares are terminals and circles are not terminals, and we call them Steiner points. And if we select these green edges, it connects all terminals together. And there are some algorithms for this problem. So a trivial two approximation algorithm has been designed. And after that, there were many works that try to improve the approximation factor for this problem. So most of these works use local search for improving the approximation factor. For example, the 11/6 approximation algorithm by Zelkovsky, the 1.65 approximation algorithm by Karpinski and Zelkovsky, a 1.55 approximation algorithm by Robin and Zelkovsky. All of these use local search, and a more complex approach used by Birka, Grandoni, Roswell, and Sanita, which achieve 1.39 approximation factor. And now it's the best known approximation factor for this problem. So let me start with explaining the two approximation algorithm. The two approximation algorithm is too simple. We just need to create a metric graph from the initial graph, and then run the MST algorithm and find the minimum spanning tree between terminals in the metric graph. And why this algorithm has two approximation factor? So let's look at the optimal solution. So for example, here we have this yellow graph, which is the optimal solution. And then we start from one vertex of this solution and pass this tree using the DFS approach. So we start from this vertex, go to the left child, and then go back, and then go to the right child. And I show that how we pass this graph using the blue arrows. So if we do this, we will make a cycle from this graph such that each edge of this tree has been passed twice. So the weight of this cycle is twice the weight of the optimal solution. And all terminals will appear on this cycle. So next, we can just look at consecutive vertices in this cycle, and for each two consecutive terminals on this cycle, we put an edge instead of the pass here. So just put edge between these two, edge between this and edge between this two. And we will make a cycle between terminals and just remove one of the edges of this cycle. So it's become a path, which is a tree. And the point is that the weight of this tree is at most twice the optimal solution. And each edge of this tree represent a path between these terminals. And since in the metric graph, we have a short, the weight of each edge is equal to the shortest path of between vertices, then the MSC on the metric graph has the cost of the MSC in metric graph between terminals is not more than this graph we have found it here, which was twice the optimal solution. So this algorithm has a top approximation factor. And now we want to see how we can improve the approximation factor for this problem. So let's first define some terms that is useful. First, define k-full component. So what is the k-full component? K-full component is a component that leaves are a terminal and other vertices are not terminal, they are starting point. And the number of leaves are at most k. So for example, here we have a t-full component, just if we look at this part. Because yes, there are three, because leaves are terminals and non-leaf vertices are not terminals, and the number of these are three. And then we define k-restricted externality. What is k-restricted externality? So if we have an externality and we cut its birth and cut this graph from its terminals, then we will have some components. For example, here we will have 4 components, and each component should be k-full component. Then the initial tree is a k-restricted external tree. And there's an important theorem by Borchers and Du. They prove that the best k-restricted external tree cost 1 plus 1 over log of k times the optimal external tree. At most cost this amount. They find the upper bound for the k-restricted external tree. And this is very important because future works try to find k-restricted external tree instead of external tree, which was easier to find. And so all of the works that use a local search for external tree, they start with the two approximate solution I explained earlier, and they're trying to use local search to make it better over time. So at each step, they have a current solution and they try to find a constant size vertices and edges outside of this solution and add them to the solution such that, and also remove some edge of the current solution such that the cost of the solution reduced by some amount. So for example, the 11/6 algorithm of Zelkowski, in this work, Zelkowski tried to get at each step, it get the current solution and try to add one new Steiner point at each step. So for example, we have a current solution here and we fix one point outside of this current solution and also three edge adjacent to this node. And we check if we add this three edge and one Steiner point to our solution, it will also remove two edges. If this change improve our solution, reduce the cost of our solution, then we will add it. Otherwise, we don't add it. And we can, for example, greedy add external points. I mean, each time select the one that reduce our solution more. So this was the idea of 11/6 approximation algorithm of Zelkowski. I want to mention that so what he was doing here, it was finding three full components, right? And three full component and added to the graph. Then Robin and Zelkowski improved this algorithm by finding k-full component instead of three full component. Make it more general. And they say that, okay, if we limit k to infinite, the approximation factor becomes 1.55. Uh, I also want to point how they do the analysis, just give it a general idea of the analysis. So they define for each k-full component, they define win and loss. So what is the win and loss? Win is the amount of cost that will be reduced from our solution if we add these k-full components. And loss is the amount that we add to the optimal solution. So what I mean, so when we are adding a k-full component, we are adding some HTML port to our solution. And we want to remove those HTML points from our solution anymore. They will be inside our solution until the end of the algorithm. So this HTML point maybe not be part of the optimal solution, and adding them will increase the optimal solution. I mean, if we assume that these HTML ports are terminals and the optimal solution is connecting them to the other terminals, then the optimal solution will increase by some amounts. And this loss is that value. It shows that if we make wrong decision, how much it will increase the optimal solution and maybe how much is bad for our algorithm. And they show that until, for example, the algorithm is by some constant factor uh, more than the current optimal solution, they can find some k-full component that has a win and increase the cost of our solution. So just you can see here, for example, we start from algorithm, which is less than 2 times opt, and at each step, we reduce our solution by win, but the optimal solution increase by loss. So that was the idea for this 1.55 approximation algorithm. Yeah. Next, I want to talk about the Einstein-Force problem, which is a generalization of the Einstein tree. So let me define the Einstein-Force problem. So again, we have a we have a weighted graph, and we have a set of demands. Each demand is a pair of vertices, and the goal is to connect the vertices of each demand. So for example, here we have a green demand and we have a red demand. And if we select these two edges, we will satisfy all demands. And again, the goal is to minimize total weight of the edge that has been selected. So there are two approximations algorithm, one by Agrawal, Klein, and Rovi, and the other one by Gomez Williamson. So the Agrawal, Klein, and Rovi actually solve a more generalization of this problem. So they solve a problem which needs to connect R passes between these vertices of each demand, and they found 2 times log of R approximation factor, which R is here 1, so it's 2 approximation factor. And also Gomez-Williamson introduced a general method, general approach for which can be applied in many problems. So one of them is Einstein-Forest, and I will explain other ones in further. But I want to mention that now I want to talk about this Gomez-Williamson approach, but it's really important to understand it. Otherwise, you cannot understand the rest of my presentation. Also, I want to mention that the Gomez-Williamson approach is primal dual, but they mention a combinatorial version of it, which I will explain it as a coloring interpretation here. So how this coloring method work? First, we assume that each edge is a curve with a length equal to weight of the edge. And we are going to maintain a forest, which at the beginning it's empty. And we are going to add edges to this forest to obtain our final forest, our final solution. And here we define active set. It's a really important term here. So active sets are basically some connected component of our forest, of the forest we are maintaining. There's some connected component of the forest such that this connected component need to extend. They need to connect to other components such to satisfy demands. So for example, at the beginning, we have empty forest here, and each vertex is a connected component itself. And you see, for example, this if we look at this connected component, it contains one red vertex which needs to connect to this other red vertex. So this connected component needs to extend to satisfy the demands for this red vertex. So it's an active set. And basically, active sets color the adjacent edges during the algorithm. So they color the adjacent edges such that until one edge becomes fully colored. For example, here this one become fully colored. Then we add this edge to our forest and we merge the connected component of endpoint of this edge. So they will go together. And we continue this until all demands are satisfied and until we don't have any active sets. So at the end, when we don't have any active sets, we have selected edges that has been fully colored, and we start the pruning phase. So in the pruning phase, we will remove redundant edges. For example, here 3 edges has been fully colored, but we don't need these edges because it doesn't help to satisfy any demand. So we remove it, and we will have only these 2 edges. Now I want to show why this algorithm is two approximation algorithm. First, I define R as the total time of coloring with all active sets in our process. Then I want to show that the optimal solution is at least R, and our solution costs at most 2 times R, and we can easily conclude that the algorithm is two approximation. So for showing the lower bound of the optimal solution, so if we look at each active set, for example, the green set here is active set. The reason that this set is active is because it needs to connect to a demand, a vertex of a demand. It means that there's a demand that have one vertex inside this active set and one vertex outside this active set. And this green active set need to grow, need to color its adjacent edges to connect the vertices of this demand. So since the optimal solution satisfies all the demands, there is a path between those vertices. So, for example, these yellow vertices, which are part of a demand, there is a path between them in the optimal solution, and this active set is coloring that path. So at each moment that an active set is coloring, is growing, it's color at least one edge of the optimal solution. So the optimal solution is at least equal to R. So, I mean, for each moment of coloring with active set, there is a part of the optimal solution that is being colored, so it's at least R. Next, I want to show that the algorithm is at most 2R. This one is a little tricky. First, I want to mention that in our solution, in our final solution, all the edges that we have selected, they were fully colored. So we want to use this to prove the upper bound for our algorithm. Just we look at each moment of our algorithm. So at each moment, we have some connected components, and we contract the vertices inside each connected component. So after contracting, each connected component is actually one vertex, and we add the edge of the final solution to this contracted graph. So here we have the edge of the final solution, and each vertex is actually a connected component in that moment of algorithm. And so some of these vertices are active, and the important thing is that the leaf of this forest, all of them are active. And why is that? Because if, for example, this vertex, this leaf vertex, is not active, then we can remove this edge. This edge is not important for us because it's not connecting any vertices of demands. Otherwise, if it needs to connect the vertex of a demand, then this vertex should be active set because there's a demand that one vertex is inside this component and one vertex outside of it. So yeah, so if this edge hasn't been removed in the pruning phase, it means that this vertex should be active. So all leaves are active, and we can use this to conclude that the total degree of active sets is at most twice the number of the active set at each moment. And it's not really hard to find this true. This one is true. You see, if we have, for example, a tree, and we know that in a tree, the total degree of all vertices is at most twice the number of the vertices, right? Now, some of these vertices are not part of the active set, they are not active sets. But we know that if a vertex is not active set, its degree is more than 2. So if we remove them from the active set and remove its degree from the sum of the degree of active sets, you see the amount that we are removing here is at least equal to 2, and the amount of we remove from here is exactly 2 because we 2 times active set. So we know that this condition holds at each moment of the coloring. And so the point is that if we continue the coloring at this step for example, duration of delta, the amount of the edges of our solution that are being colored is delta times the total degree of active sets. For example, you see here that we are coloring the final solution here. We get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. We are coloring the final solution in 11 places. So if we continue with in the delta seconds, we will color 11 times delta portion of the graph. And the number of the active sets is 1, 2, 3, 4, 5, 6, 7, 8. So 11 is less than the 2 times 8, actually. So yeah, so we can say that in amortized, the amount of the value that are being added, the amount of, the amount of time that a set is active is at most, sorry, the amount that an active set is coloring our final solution in amortized is twice the time it was active. So in total, our solution is at most 2 times R. Okay, so this will complete the proof, and this is the best algorithm for Steiner-Forest problem. Next, I want to talk about the price correcting Steiner-Forest or PCSF, which is a generalization of the Steiner-Forest problem. In the price correcting Steiner-Forest, we again have a weighted graph and a set of pair of vertices that we call them demands, similar to the Steiner-Forest. Here, in addition, each demand has a penalty, and we can decide for each demand whether connect the vertices of the demand or pay the penalty and don't connect these vertices. And the goal is to find the forest such that the weight of the forest plus penalty of the demands that are not satisfied by this forest is minimized. So for example, here we have selected this edge and we didn't connect the red pair, so we need to pay the penalty of that one. So there are some T-approximation algorithms for this problem. Haji Aghay and Jane give a primal law algorithm which can be explained using the coloring method. Also, Gupta, Kahneman, Leonardo, Ravi, and Schaffer and give a cost sharing algorithm for this one. And also there's a Haji anti-approximation algorithm using iterative rounding by Haji Aghay and Nasri. And also there's a randomized LP rounding algorithm with 2.54 approximation factor by Haji Aghay and Jane. And recently, we have developed a approximation algorithm using an iterative approach, which was a joint work with Ali Ahmadi, Imam Gholami, Muhammad Haji Aghay, and Muhammad Mahdavi. So first I will explain the primal DAL algorithm of Haji Aghay engine, and then I will explain our two approximation algorithm. So the tree approximation algorithm by Haji Aghay engine is similar to the algorithm of Steiner forest. It's actually used the algorithm for Steiner forest as a base, and we call the algorithm for Steiner forest as aesthetic coloring from now on. The problem is that here we have each demand has a penalty and we need to consider it. So we don't want to, for example, connect a pair of vertices by paying too much cost for the edge that we have selected when we can pay penalty and don't connect them. So basically, we want to bond the amount of color we use for connecting each pair. So for this, we define dynamic coloring. In the dynamic coloring, we give unique color to each pair, and we limit the color of each pair by the penalty of that pair. So we run the static coloring, the algorithm of Stein forest, and each moment of coloring with the active sets, we assign the color to a pair such that the active set cut that pair. So for example, here we have an active set, we have the blue active set. This one is active set because it wants to connect red vertices. And this active set only cuts red vertices. It doesn't cut green vertices. And by cut, I mean that one vertex of this pair is inside the active set and one vertex is outside of it. So we only can assign the color of this active set to the red pair. But the problem is that sometimes one active set has cut multi pairs, and we don't know how to do this assignment. So for designing the tree approximation algorithm, we can just assign, I don't know, greedy, arbitrary, anything works. But because we want to use this algorithm to design the tree approximation algorithm of ours, so we need to do this assignment more carefully. So we introduce a new graph and find the maxfill on this graph to find the assignment. In this graph, we have a source, a sink, and two parts of this graph. So in the left part, we have one vertex for each subset of the vertices of the initial graph. And we had an edge from source to each subset to each set S, such that the capacity of this edge equal to the total time that this set was active. So if, for example, set S wasn't active set at all, we can remove that vertex. But if it was active, we add the edge from source to that vertex, and we put the capacity equal to the total time that this set was active. So in the right side, we have a sink and we put one vertex for each pair, and we add an edge from each pair to sink with capacity of the penalty of that pair. Finally, for each set and for each pair, we add a edge with a capacity of infinity from that set to that pair if the set is cutting that pair. And then we run the max flow, and the max flow should fill all the vertices in the left, all the edges in the left side. Then the amount of flow in the middle show the assignment, show that how much we are assigning the color of the set, for example, S to pair IJ. The amount of flow in this edge will show this to us. Also, the amount of flow in the right edges show us the dynamic coloring. They show that how much we use the color of the pair IJ. And it should be less than PIJ, of course. So we use this assignment, we run the static coloring, and so in static coloring, we may have, if you remember in the static coloring, we find edge that are being fully and edge that are fully colored, and we add it to the forest and continue the process. But here we have another event. So it's possible that if we increase the if we color with active set, we cannot find an assignment, find a valid assignment, because here you see each pair has a capacity, and we may reach the capacity and we cannot use the color of the pair. So in this case, we call the pair that we run out of its color, pair that reached its capacity as a tight pair, and we pay the penalty of tight pair, and we deactivate some active set because pair become tight and we don't need to connect them. So some active set may become deactive, and we deactivate them and continue the process. At the end, we find all tight pairs, and we want the number of tight pairs become minimal. It's important for, in the two approximation algorithm. I mean, we do this assignment such that the assignment on the max value such that the number of pairs that has reached the capacity is minimal. And then we pay penalty for tight pairs, and we show that the force that we have find connect other pairs, the pairs that are not tight. And why this is true, it's easy to see. Because if a pair is not tight and it's not connected in the forest, then the connected components containing the vertices of this pair, they should be active. They have a still color because the pair is not tight, and they haven't satisfied the demands of that pair, so they will be active. So the process has not finished yet. So at the end, every not non-tight pair is connected, and we will remove redundant edges similar to Einstein forest. Then we want to show that this algorithm is the approximation algorithm, and again we define R as total coloring moment of active sets, and we say that optimal solution is at least R, and it's easy to see why this is true. I mean, if you remember in Einstein first, we said that each active set is cutting one edge of the optimal solution. Here we can say similar thing. We can say that either each active set is coloring one edge of the optimal solution, or if it's not coloring the one edge of the optimal solution, then there is a demand. There's a demand that optimal solution is paying its penalty. I mean, if let me lower it. If, for example, we have an active set here, and the color of this active set has been assigned to a pair here. Since this active set is not coloring an edge of the optimal solution, so there isn't any pass between the pair of between these vertices, which means that the optimal solution is paying the penalty for this pair. And since we don't use the color of this pair more than its penalty, so we can say that we can, assign this coloring with active set to the penalty that optimal solution is paying for this pair. So the optimal solution is at least R. Then we want to say that our forest is at most 2R, the forest we are selecting. The proof for this one is completely similar to the proof for Einstein forest. It's not different. The point is that here we have another thing. We have a penalty, and we can show that, okay, the penalty is also at most R, which if we prove this, we can conclude that our algorithm is T approximation. And why this one is true? Why our penalty is at most R? Because we only pay penalty for tight pairs. And we know that for each tight pairs, we have assigned the color of active set to these pairs equal to its penalty there, because we use all of this color of those pairs. So the total penalty of tight pair is not more than the total coloring of all active sets. So yes, we can say that the penalty is at most R, and we can conclude that the algorithm is tree approximation. Mm. And I want to just mention the dual uh, natural LP of the Pascal forest, because you see this problem was actually based on primal dual approach. And you see that here it's the dual LP of the Pascal forest, and the value of via Sij is actually the amount of coloring with active set S that has been assigned to pair ij. And we can see two constraint here. The first constraint is actually the one that we had for Stein-Forest 2. It said that it's saying that when we say that if an edge becomes fully colored, add it to the forest and merge its connected component, we don't want to, uh, color an edge more than its weight. That's this constraint say. So basically, by adding fully colored edges to our forest and merging its component, we make sure that this constraint never been violated. And we have another constraint here. We call it pair constraint. This one is actually the one that we say if the color of one pair is fully used, just call it tight pair and pay its penalty and don't assign any color to this pair. So here by making sure that we don't use the color of each pair more than Pij, we make sure that this condition never been set and never been violated. So basically, this algorithm is finding a dual solution such that uh, none of these constraints will be violated. And our final solution is at most 3 times this dual solution. And uh, so we can easily conclude that our solution is tree approximation. Next, I want to talk about R2 approximation algorithm for path correcting Steiner forest. So I want to mention that this algorithm uses the tree approximation algorithm that I have explained. So basically, I start with the running the tree approximation algorithm, and then if no penalties are being paid by that algorithm, we just return that solution, and it's actually a two approximation. It has two approximation solution in this case. Otherwise, for tight pairs, it's find in the two approximation algorithm. We pay the demand, pay the penalty for those demands for those tight pairs, and we remove the penalty of them. I mean, we don't need to connect them anymore, and we recursively call this algorithm again. So again, we will call the PCS, the tree approximation algorithm on it, and and find a new solution. This new solution may find new tight pairs, and we pay the penalty for those new tight pairs, and we will do it again. So this algorithm will have multiple steps, and the last step doesn't pay any penalty, and we will return there, finish it there. And at the end, we will return the best solution among all the solutions we have found. And uh, so why we use this approach? Because the problem was that in the tree approximation algorithm, we are paying the penalty of tight pairs, but we also assign the color of those active set to those tight pairs. So basically, those tight pairs are coloring edges, and we may select edges because of those coloring. So this tight pair, despite that, the fact that we are paying the penalty, we may select edge because of them. So this doesn't make sense actually. So if we want to pay penalty for some pairs, just pay the penalty and don't try to connect them anymore. That's the idea behind of this algorithm. So for proving the approximation guarantee of this algorithm, we use induction. And so the induction base is basically the last step, the step that we don't pay any penalty. So we can easily see that this step give us a two approximation solution for the for the instance given at this step. So what it means, it means that I mean, why this one is true? Because if you remember, in proving the three approximation guarantee of the previous algorithm, we say that our force is at most r 2 times r, and our penalty is at most r. So three times the optimal solution at most. But if the penalty is 0 and our force is 2 times r, so it becomes two approximation. So the last step give us two approximation solution for the last step instance. But if we are paying the penalty, what it means here? I mean, for general case, we want to prove the induction step. First, I want to see what is the induction hypothesis. So the induction hypothesis is say that you see here we pay penalty for tight pairs and the removal of demands of those tight pairs. And then we have a new instance. We call it recursive instance. And then we run our algorithm on this recursive instance. So using induction hypothesis, we can say that this recursive call give us a two approximate solution for the recursive instance, not for the initial instance. That's the induction hypothesis. It says that for the new instance, we have a two approximate solution. And we call uh, this solution achieved by the recursive call as the IT solution, and we call the solution achieved by tree approximation algorithm as PCSF3. And now we want to say that the minimum of these two solutions has at most 2 times the optimal solution cost for the initial instance. So first, let me define some terms. We have a single edge set and multi-edge set. Basically, we look at the optimal solution. For here, we have the optimal solution. And for each active set, if it cuts exactly one edge of the optimal solution, we say that it's a single edge set. And if it cuts more than one edge, we say it's multi-edge set. And then we want to classify tight pairs. I want to remind that we define R as total time of coloring for all active set, and we say that, okay, PCSF is at most, the forest of PCSF3 is at most 2R, and its penalty as most R, which is make it at most 3R. Or here we just say that, okay, PCSF3 is at most 2R plus the penalty of tight pairs. So 2R for the forest and penalty of tight pairs that it pays. Then we divide the tight pairs, the pairs that PCSF3 pay the penalty. We divide the tight pairs into two classes. So first class contain pairs that connected in the optimal solution, and the second class contain pairs that optimal solution pay their penalties. We also divide the first class into two classes. So C1 contain the total time of coloring with active set with pair in the first class. I mean, tight pairs that connected in the optimal solution. So C1 is total time of coloring with active set. That cuts exactly one edge of the optimal solution. I mean, they are single edge set, and they color assigned to this class, the class of C. This is C1, and C2 is the multi-edge set active sets, and that they color is assigned to class to pair in the class C. I mean, class of tight pairs that connected in the optimal solution. This is C1 and C2. And yeah, so this classification is really important. So let me go further. Now, if you remember, for the recursive instance, we remove penalty of tight pairs, which means that for the recursive instance, we don't need to connect tight pairs together. Now I want to find a bond, upper bound for the optimal solution of the recursive instance. To find this bond, I actually find a solution for the recursive instance. And then I say that, okay, the optimal solution for the recursive instance is at most equal to the cost of this solution that I have found for the recursive instance. So how I find the solution for the recursive instance, I say that, okay, get the optimal solution. Then I remove P from it. So what was P? P was the tight pairs that optimal solution was pays the penalty. Because in the recursive instance, we have already paid penalty of tight pairs and the penalty is 0. So we don't need to pay them from, and we remove it from the optimal solution. And also, I want to remove some edge of the optimal solution. So let's look at this image. Assume that this graph is the optimal solution. And we have an active set here that cuts one edge of the optimal solution. This means that this active set is a single edge set that we have defined here, single edge set. And its color is assigned to a tight pair. So for example, its color is assigned to the blue pair, which was a tight pair. First, I want to prove that all pairs that are being cut by this active set are tight. I mean, look at this red pair. I want to say that the red pair should be tight. If the red pair is not tight, we can assign the color of this active set to the red pair instead of blue pair. Then the blue pair won't be tight. And we can color with blue pair further because it was a tight pair, so it wasn't connected. So we can connect them now. So by this, by this change, the number of tight pair will be reduced, which cannot be happen because the max flow that we had for the T approximation algorithm. So all the pairs that are being cut by this active set, this active set is tight, and since this active set is cutting only one edge of the optimal solution, we can remove this edge. We can remove this edge, and it will only disconnect tight pairs in the optimal solution, which we don't care because we have paid the penalty and we don't need to connect them. So C1, if you remember, was the total time of coloring with tight pairs that connected in the optimal solution and cut exactly one edge of the optimal solution. So we can remove edges in amount of C1 from the optimal solution and don't disconnect pairs that are not tight from the optimal solution. So we can remove them and we will still have a valid solution for the recursive instance. So we can conclude that the optimal solution for the recursive instance is at most opt minus C1 minus P. Okay. Now we have proved this one here. And since the induction hypothesis says that the recursive instance is at most 2 times the optimal solution of the recursive instance. And we also need to pay the penalty for tight pairs because we first pay the penalty for tight pairs and then call the recursive instance. So the recursive instance is at most, its cost at most this amount, which we can replace the optimal recursive instance with this one, with this bond we have here. So we will get this bond for the recursive instance. Okay. Also, if you remember, for the tree approximation algorithm, we say that the optimal solution is at least R. Okay. Here we want to give a better bond. We say that it's at least R plus C2. I want to remind that C2 was tight pairs that were connected in the optimal solution and cut at least two edges of the optimal solution. So why this term is true? Because you see, in the proof of the optimal solution, we say that each active set is either uh, assigned to a tight pair, assigned to a pair that optimal solution pays penalty, or it cuts one edge of the optimal solution. But we know that for the C2 amount, the active sets are cutting more than one edge. They are cutting at least two edges of the optimal solution. So we can get better bound for the optimal solution, which is equal to this amount. And also we had this upper bound for the PCSF theory. We mentioned that PCSF theory is at least 2R for the forest plus the penalty is paid, which is C plus P. I mean, if you remember here, we divide tight pairs to C and P. So C plus P actually is the tight pair, total coloring with tight pair or total penalty of tight pair, they are same. And we just use this bond for the optimal solution here, and we get this bond for the PCSF tree. Now we have this two bond for the one of them for PCSF tree and one of them for the instance returned by the recursive call. And we say that the minimum of them is at minimum of them is less than the average of them, and average of them is at most 2 times opt. So the minimum of them is at most 2 times opt, and the minimum of them is to approximate solution. And that's the end of the algorithm for PCSF3, PCSF to approximation algorithm for PCSF to PCSF. Next, I want to talk about price cartesian or PCST, which is a generalization of the Schneider tree, and it's also price cartesian Schneider forest is a generalization of the price cartesian tree. Let's define the problem, the PCST problem. So we have a weighted graph and a subset of vertices as terminals, similar to a Schneider tree problem. Here, each terminal has a penalty, and we either should connect the terminal together, or I mean, here we talk about the rooted version, but the rooted and unrooted are same. So in the rooted version, we have a root, and we either want to connect each terminal to the root or pay the penalty for that terminal. So, for example, here we have this one is root, and we connected these two terminals to this root, and we didn't connect this terminal to the root and pay its penalty. And the goal is to minimize the total weight of the selected edges. So, for example, these edges here, plus the penalty that we have paid for the terminals that are not connected to the root. So the general approach, the general technique of the Gomez-Williamson that we mentioned for the Einstein forest, give a two approximation algorithm for this problem. We will explain it later how they find this. And then Archer, Botany, Hajiagay, and Karlov give a 1.96 approximation algorithm for this problem. And recently, we designed algorithm better than 1.8 approximation factor, which was a joint work with, again, Ahmadi, Gholami, Hajiagay, and Mahdavi. So let me first explain the two approximation algorithm of Gomez and Williamson. So the idea is similar to the two approximation algorithm for Einstein forest or three approximation algorithm for Paris-Cartesian forest. And so the difference of this algorithm and the Einstein forest algorithm is that here, where terminals has a penalty, and again, we need to assign color to each terminal, and we need to limit the amount of color we used for each terminal. So you see, we have similar thing for PCSF, I mean Paris-Cartesian forest, but in PCSF, each demand has one color, each pair has a color, and we don't know how to divide this color. I mean, how much we use it on this endpoint on this vertex of the demand or how much we spend on the other vertex of the demand. But here, each penalty is assigned to one terminal, so it's more easier than the PCSF. We know we give we can look at this penalty as a potential. We give each terminal a potential equal to its penalty, and each time active set is coloring its adjacent edges, we reduce its potential, and if two active sets merge together, we adopt their potential together, and we continue this process until there are no active sets. And also when an active set run out of the potential, we call it dead set, and we don't, deactivate it and don't color with that active set anymore. And at the end, we look at the dead sets, and for any dead set that cut exactly one edge of the solution, we remove that edge and that dead set from our solution. So for example, here, you see, for example, we have a root here and a live vertex here. The live vertex, a vertex that never got dead and connected to the root. And there were some dead sets here, for example, blue one and the red one. For the blue one, because the live vertices has passed through them, they cut at least two edges of the solution, so we don't remove them. We'll connect them to the root too, and all of the vertices inside them. But the red ones, they're cutting only one edge of the solution. We can remove this edge and all of the subset, it will only disconnect the sets. So we will remove them and don't connect them. This makes the algorithm to approximation algorithm. So why it's two approximation algorithm? Again, we define R as total coloring moment of all active sets, and the same thing that we said for PCSF, we can say here for optimal solution. We can say optimal solution is at least R, because each time we color with active set, we either connecting the terminal of that active set. Each active set, the color is assigned to one terminal inside it. If we connect that terminal to the root, so we are coloring edge of the optimal solution. And if the terminal is not connected to the root, so the amount of coloring that we are using the color of that terminal is not more than the penalty that optimal solution pay for that terminal. So the optimal solution is at least R. And we want to say that our solution is at most 2 times R. And you see, we say that always the force we are finding, or the tree we are finding here, it's at most 2 times R. And this is correct here too. But the point is that if we don't connect a terminal to the root, we don't use its color to connect other vertices. You see here, for example, the red sets, the red vertices were dead set, were inside the dead set, and we remove them from our solution. And we don't use the color to connect other vertices. So we can say that our final tree, it's at most 2 times the total coloring with vertices with terminal that has been connected to the root. So we can bond our tree like this. And also we say that for vertices that has not been connected to the root, because they were tight and they were dead sets, it means that we have used all of the colors and they haven't connected to the root. So for each time that we have used the penalty that we are paying is proportional to the time of coloring with those terminals. So basically we are dividing terminals in 2 parts. So one part is terminals connected to the root, so we pay 2 times for coloring with these terminals, and one part is vertices that are not connected, terminals are that are not connected to the root, and we pay at most equal to the coloring time with these terminals. So our solution is not more than 2 times R, and the algorithm gives us a two approximation algorithm. And next, I want to explain our 1.7994 approximation algorithm for PCS3. So let me first introduce a modification on the previous algorithm. So we define a parameter beta, which is between 1 and 2. And we divide all penalties by beta. It means that we are reducing the penalties, so we will so the color of terminals will run out earlier. It means that the number of terminals that are connected will be less than the previous approach. And why we do this modification? So let me show the analysis of previous algorithm. So in the analysis of first algorithm, as I was explaining, the only place that we have a coefficient 2, I mean, for each time of coloring, we are paying 2 times the amount of color we are using, is here for connecting the vertices. So this has coefficient 2, but for the paying penalty, it has only coefficient 1. So because we are paying too much penalty for, we are paying too much cost for connecting vertices, we are reducing penalty to connect less vertices. And while this will increase the coefficient of this one from 1, it will become beta actually, but because beta is less than 2, the algorithm remains to approximation. And so now I want to explain our algorithm. It's iterative algorithm. Again, it's similar to the algorithm we had for PCSF, but it's a little more complicated. So we run the Gomez-Williamson algorithm, but with parameter beta. And if this algorithm is paying penalty for some pairs, for some terminals, we pay their penalty. Actually, the Gomez-Williamson pay penalty for some dead set, not all dead set. If you remember, for only dead set that cuts one edge. But here we pay penalty for all dead set. I mean, we don't care if it cuts one edge or more than one edge of the solution. We pay penalty for all dead sets, and we say that, okay, now we don't need to connect the terminals in the dead set. We don't need it. I mean, we don't have a demand to connect them. We remove their demands, we remove their penalty. Then for the remaining terminals, we connect all of them together using the best algorithm for Steiner tree. So we will have another solution here. So if we call the first solution GW solution, the solution achieved by the Steiner tree algorithm is this solution. And also, if we had a new instance because we have removed penalty for some terminals here, if we don't remove any penalty here because the Gomez-Williamson doesn't pay any penalty, doesn't have any dead set, we are fine. But if we have some penalty here, which means that we have created new instance here, we call it recursive instance, and recursively call our algorithm on this recursive instance. And the solution achieved by this recursive call, we call it IT solution. Again, similar to the PCSF algorithm, we return the best solution among all of the solutions we have obtained. So similar to the PCSF algorithm, we can bound the optimal solution and Gomez-Williamson solution. So the Gomez-Williamson solution bound has been a little different because we used parameter beta, but it's not really hard to find the bound. And the IT solution is also a little different. I mean, if you remember in PCSF, we say that the recursive call give us to approximate solution for recursive instance. But here we say that it gives us alpha approximate solution for the recursive instance. I mean, we don't know alpha at the beginning, but at the end, we want to find alpha such that alpha is the approximation of our algorithm. And we say that, okay, using induction hypothesis, the recursive call gives us alpha approximate solution for the recursive instance. And so we can bond the Goldman-Williamson solution, IT solution. Next, we want to see how we can bond the ST solution, or the solution obtained by running Einstein tree algorithm. So we want to find the instance for the Einstein tree algorithm. I mean, Einstein tree instance. I mean, so in the Einstein tree instance, we want to connect all the remaining terminals. I mean, if you remember, we paid the, let me just get here. We pay penalty for all the vertices here, and then connect other vertices, or we call it live vertices using Einstein tree. We want to find a instance that connect all the live vertices together. And then we say that since the best algorithm for HTTP now has 1.39 approximation factor, if we run that algorithm on this instance, it will give us 1.39, at most 1.39, the instance that we have, the solution that we have find for those, for connecting those terminals. Okay. So now we want to find the instance, find the solution that connect all the live vertices, all the not all the vertices that wasn't in the dead set, and connect a solution that connect all of them together. So how we find this? We first take the solution of the optimal solution. I mean, the tree of the optimal solution of yeah. Yes, the tree of the optimal solution. And then we say that, okay, live vertices, maybe for example, something like this, it contains uh, some vertices of the optimal solution and contains some vertices outside of it. So we need to connect these vertices outside of the optimal solution to these vertices. And how we do this? We do this similar to Gomez-Williamson. We find out how the Gomez-Williamson connect these vertices together, and we pay amount that Gomez-Williamson pay to connect those vertices. So basically, we take the optimal solution and connect other vertices, similar to the way that Gomez-Williamson connect them together. And also, so in this way, we connect all live vertices, and we also need to pay penalty for the dead vertices, which is similar to the paying penalty for tight pairs in PCSF. So now, in this way, we can bond the forest, the ST solution, or HTTP solution, and we have bonded all of, let me remove this. We have bonded all the three solutions that we had, the GW solution, SC solution, and IT solution. Then we rewrite this bonds as something like this: alpha times opt plus some extra value. And we take the weighted average between these three bonds. We want to show that we can find some weights such that this extra value becomes 0. So we will have some inequality, and we want to find alpha, beta, and weights for each solution, such that if we take the weighted average of these solutions, the value become at most alpha opt, or this extra value becomes 0 or negative. And we find out that if we put alpha equal to 1.7994 and beta equal to 1.252, we can satisfy these inequalities, and the minimum, then we can prove the induction step and prove that our algorithm is 1.7994 approximation algorithm. Next, I want to talk about the KMST problem. So in the KMST problem, we again have a weighted graph, and in addition, we have a value k, and we want to find a tree containing at least k vertices such that the total weight of the edge of the tree is minimized. And there are many work on this problem. It's a start with square root of k approximation algorithm, and it's go to log squared, then log approximation, then 17, then 3, 2.5 plus epsilon. And now the best algorithm is two approximation, has two approximation factor by Navin Garg. So I want to first explain the three approximation algorithm by Garg, and then this 2.5 approximation algorithm and 2 plus epsilon approximation algorithm make a little change on this one and improve the approximation factor. And then this one is a little bit, there, all of them are has a base algorithm that is same, but they have just some different technique for the last part of the algorithm. So let me start with the three approximation algorithm by Navin Garg. So the algorithm is a fixed root. I mean, fix one vertex, say that, and they say that, okay, we assume that this vertex is part of our solution. And we want to find the best tree containing this root. Then we want to find the smallest p, if such that if we give penalty p to all vertices and run the Gomez-Williamson algorithm for price collecting Schrödinger tree, then the component of the root has at least k vertices. And if the connected and we find the smallest p for this one, and if component of the root has exactly k vertices, we are fine. We actually have a two approximate solution. And because and why is that true? Because we know that the optimal solution is at least kp. We can easily prove that, and we can also say that our solution is at most 2 kp, because similar to the proof of the Schrödinger tree in classical Schrödinger tree. So if the size of the component of the root is exactly k, we are fine. But the problem is that its size may be more than k. I mean, for example, if we set penalty equal p minus epsilon, the number of vertices in the component is less than k. But if we set it equal to p, then it's become too much large. And for example, it become value k prime, which is more than k. And we can only say that, okay, our solution is two, I mean, the tree we have found costs 2 times k prime time p, which can be too large, and it's not good for us. We need to remove some vertices to fix this. So now consider the solution with penalty p minus epsilon and the solution with penalty p. So the solution with penalty p minus epsilon, we can call it old solution, and the solution with penalty p, let me write it. So we call this old solution, and we call this one the one with penalty p new solution. So the old solution contain less than k vertices, and the new solution contain more than k vertices in the component of the root. So what we do, we choose the intersection of these two solutions, which obviously have less than k vertices. And we can say that these two solutions only differ in one place. And it's not really hard to see that. I mean, for example, we can change edge of the graph with different epsilon values. So it makes sure that if we increase penalties by epsilon, only one event will change. And how? So what do I mean by only in one place or one event they change? So There are two cases for this. The first case is that here, for example, a new component will be added to the component of root. It means that, for example, if we look at this edge, this component become dead set before it connected to the component of root. So in the pruning phase, we have removed this set. But because we have increased the penalties by epsilon, this component will be merged to the component of root before it become dead. So we don't it won't become a dead set, and we don't remove it in the pruning phase. So the number of vertices will become more than k. This is the first case. The second case is that for example, here in the old solution we had red edge, but a new edge will become fully colored before this red edge. For example, the green edge become fully colored before red edge, and this will make that we never choose the red edge because it makes a cycle. So I mean, so basically, one edge replaced by the other edge in the second case. And so let's see what we can do in the first case. So in the first case, we have this component of the root, which contain less than k vertices, and we had the other component, which if we add it to the first component, it contains more than k vertices. And we want to do a recursive approach to keep exactly k vertices from all of this. So we look at the second component, and we know that this component has been formed from two active sets merging together. So for example, this was the last two active sets that merged together and formed this component. And also this edge is the last edge, sorry, is the last edge that selected in this component. So here, between these two components, one of them is near the root and the other one is far from the root. And if the near component is enough for us, it means that adding this to the component of the root will make at least k vertices. We remove the far component completely and do this recursively on the near component. And if the near component is not enough, it means that selecting all of these vertices inside it plus vertices in the root component will not add up to k. Then we select all vertices inside the near component and then recursively call this approach on the far component. So by this recursive approach, at the end we will have exactly k vertices, and we can show that the output is actually heading to approximation up. But the second case is more complicated than the first one. First, I want to mention that why, if we want edge replaced with another edge, the number of vertices may become more than k. So why this happens? Because it's possible that around this green edge, the new edge that we have added, there was some dead set, for example, the one that I showed here. There was some dead sets that because this dead set cut one edge of the solution before we add the green edge. It only cut one edge of the solution. We are removing this dead set in the pruning phase. I mean, if you remember the Paris-Cartesian tree algorithm, in the pruning phase, we remove the set that cut exactly one edge of the solution. So we will remove this set. But now that green edge has been added, this dead set actually cut two edge of the solution. So we won't delete it, and the number of vertices in the component become more than k. So we need to do the same things, do the same recursive thing that we do in the first case here for the data set that we have removed. And so this one is not really hard, this part, but the problem is that, you see, we get the intersection of the uh, old solution, I mean, solution for penalty p minus epsilon, and the new solution, I mean, the solution achieved by setting penalty equal to p. Because we get the intersect of these two solution, and this green edge and red edge is not a part of any, I mean, is not part of the intersection of this solution. One of them is in the old solution, the other one is in the new solution. So basically, these two components will be disconnected in the intersection of these two solutions, and we need to connect them. We need to add edge between these two components to connect them. So the problem is that in the theory approximation algorithm of Navier, uh, the Navier can bound this one edge by optimal solution. So that okay, this edge is not more than optimal solution. So we need one factor for this new edge and two factor for the other edge of the solution. So it's at most three approximation algorithm. But future works try to give a better bound for this last edge. So, for example, the 2.5 approximation algorithm and 2.5 approximation algorithm by Arya and Ramesh, and also this 2 plus epsilon approximation algorithm by Aurora and Karakostas improve the bond for this last edge. So let me just explain the 2 plus epsilon approximation algorithm. So, and let's see how it's improved the last step. They say that instead of fixing one vertex, let's fix 1 over big O of 1 over epsilon vertices, so it's constant. Let's fix this amount of vertices. And they say that if we look at the optimal solution, we can find big O of 1 over epsilon vertices such that the distance of other vertices to the selected vertices is at most epsilon times the cost of the optimal solution. So if we find this, if we fix these vertices, if we find these vertices, and then uh, run the same approach for the KMST, such that this all of these fixed vertices in the they are all in the component of the root here. Then the last edge that we are selecting, it's cost at most epsilon times optimal solution. So in total, our cost is at most 2 plus epsilon times the optimal solution. Next, I just want to briefly discuss the two approximation algorithm by GAR. And in this algorithm, Navier works on the unrooted version, and again, it assigned penalty p. I mean, it find the smallest p that if we assign penalty p to all vertices, there is a component. It's not the root component because we don't have root here. There's a component with k vertices, and so it finds the solution on that component similar to the uh, previous algorithm. But the point is that it's not finished yet here. So you say that, for example, we find the smallest p that the one component has at least k vertices. So in this case, after we run this Einstein theory problem, this price collecting Einstein theory with penalty p, we will have some components. For example, this is one component, this is one component, and this is the component that contain k vertices. So now let's run this KMST algorithm recursively on each of these components, on this one, and also for the component that has k vertices. Look at the last two components that forming this component, and run the KMST algorithm for each component of each of these components separately. So it's basically find one solution and divide the graph into different parts, and then run this algorithm recursively on each part. And they prove that if we do this, at the end, we have a two approximation algorithm to approximate solution. That's it. And at the end, I want to just point out to K-Stein tree problem, which is a generalization of KMST problem and also generalization of the Eshlein tree. So the problems say that we have a weighted graph and a subset of vertices that we call it terminals, and also a value integer k, and we want to find a tree that span k terminals, and we want to minimize the total weight of the edges that we have selected. So there was a 4 approximation and 5 approximation algorithm for this problem, but Bateni, Hajiaghi, and Liagat have proved that this problem is same with KMST. I mean, they provide approximation preserving reduction from K-Stein tree to KMST. So any approximation algorithm for KMST works for this problem. Yeah, and no future work will needed for this problem. Yep. So that's the end of my presentation. I hope you have enjoyed and it was useful for you.